So chapter 11 is all about our power series. In our previous section 11.1, we used our power series to define our Taylor polynomials, which we then used to approximate values of functions. In this section, we're going to look at other properties of power series. What I'd like to bring your attention to first, though, is to look at our geometric series. So remember, our geometric series had our a sub k as being some ratio to the kth power. So if we expand out our geometric series, we have 1 plus r squared, assuming we're starting with k is equal to 0. And then the value of our geometric series is a over 1 minus r. In this case, our a value is simply 1. So the value of this geometric series is 1 over 1 minus r. And this series will converge as long as the absolute value of r is less than 1. So why don't we replace this r, which in a geometric series is some constant that does not change, with x, which is a variable and can change. So x is simply any real number. Expanding the series out, we have 1 plus x squared, and so on. It's still a geometric series. It's still going to converge to 1 over 1 minus x. However, it converges as long as the absolute value of x is less than 1. So remember, x is not constant. X varies. So how we want to think about this special power series is think about it as if it were a function. And this function is going to be equal to 1 over 1 minus x, provided the x's that we put in, that their absolute value is less than 1. So you can think about the absolute value of x minus 1 as being the domain of our function. And that would be the goal for the first part of, well, actually, for this whole section, is to come up with this function as a power series and to find the x values so that the series converges. These x values will be called the interval of convergence. In this particular case, my interval of convergence goes from -1 to 1. Or you could write it as the interval -1 to 1. The center for this particular power series is 0. And then we have this new vocabulary. This would be our radius of convergence. In our case, for this example, my radius of convergence is 1. So what your radius of convergence is your center to an endpoint. So notice in this interval from -1 to 1, the center of this interval is 0. So if I add 1 to 0, I get the endpoint 1. If I subtract 1 from 0, I get the endpoint -1. But the radius of convergence is the distance from the center to either endpoint. And we use r. This is not the real number r. This capital R stands for radius of convergence. So in this case, our radius of convergence is 1 because the distance from the endpoint to the center is 1. Looking at the more general power series, again, this is what we discussed in our previous section, where the center is any a value. It doesn't have to be 0. We have that a and our c sub k's. They're just real numbers. Center is a. Coefficients are c sub k. So we're just reviewing our power series from the previous section and then adding in this new vocabulary on interval of convergence and radius of convergence. So in this case, x is just some variable. The x values where the series converges, again, you can think about this as the domain, would be our interval of convergence. And then the radius of convergence, which we use capital R, is going to be the distance from the center to the boundary of the interval of convergence. So it's just the distance from the center to either endpoint. So the key is to figure out the x values that make our series converge. And what we're going to do is go back to Chapter 10, where we talked about absolute convergence. So if we looked at the absolute value of a series, and if that absolute value of the series converges, then our series converges absolutely. If we look at that property, then that's what we're going to do to find the interval of convergence, or rather the x values, so that our series converges. So we usually use ratio or root test on the absolute value of our series. However, we have to check the endpoints on our interval of convergence. When we, and you'll see when we do an example, when we use the ratio or the root test, we will get an interval, but it will not include the endpoints. So we still have to check to see if the x values at the endpoints of our interval of convergence will also make the series converge. This should all be clearer when we look at example 1. So remember, the whole point is to find the interval of convergence, the x values that make this series, x to the k over k factorial, converge. Now typically we would use the ratio or the root test. Whenever I see a factorial, I think ratio. And we're going to be looking at the absolute value of this series. So when we take the limit as k goes to infinity, using our ratio test is going to be the absolute value of x to the k plus 1, so it's the k plus 1 over the k terms. Now I can't leave off the absolute values because remember, I don't know what x is. X could be negative. And this is over k plus 1 factorial, all over x to the k over k factorial. Now I'm going to rewrite this. I wonder if I have enough space. So that it's x to the k. The k plus 1 means it's x to the k times k, or x to the k times x, sorry, over k plus 1 factorial times the reciprocal, which would be k factorial over x to the k. So you can see that the x to the k will cancel. And I'm going to expand out the k plus 1 factorial so I can cancel the k factorials. Something to also note is I still can't get rid of my absolute values because I don't know what x is. So this is going to be x over k plus 1 times k factorial times k factorial. And the k factorials cancel. Now I have the limit as k goes to infinity of the absolute value. And now here the absolute values are not needed on the k plus 1 term because remember, our k values are 0 or some positive number, so k plus 1 will never be negative. I only really need the absolute values on the x. So again, the k plus 1 does not need the absolute values, but you can keep them on. It's not going to hurt anything. And now this limit is saying what happens when k goes to infinity. Notice that it says nothing about x. So we can treat x as if it were a constant and bring it out into the front. Now you don't have to, but sometimes it's nice to bring it out so it doesn't distract us from evaluating this limit. So now I could see the limit of 1 over k plus 1 is simply 1 over infinity, which is 0. I'm going to go all the way back up here. And note that this limit is equal to the absolute value of x is still there, but the limit is 0. So I have to figure out what x values I can put into my original series so that that series converges. And we're going to go back to the property that the series converges when the absolute value of r is less than 1, but then we replace that with x. So if we simply set this less than 1, we see that it really doesn't matter what the x is. Because I'm multiplying this by 0, this product will always be 0. 0 is always less than 1, no matter what x value I put in. So this is a special case where this will converge for all x. Right? If x is 1, -1, a million, 0.25, doesn't really matter since I'm multiplying it by 0. It'll always converge. So my interval of convergence can't spell, is going to be -infinity to +infinity. I can put in any x value in that interval and my series will converge, which means my radius of convergence is +infinity. Let's look at another example. So with v, we have this alternating series. I see all these k's, exponent k, so I'm thinking maybe I'll try root test. And remember, I'm getting rid of that -1 because I'm looking at the absolute value of -1 to the k. X to the k over 5 to the k, I'm going to write that as x over 5 to the k since they have the common exponent k. And since this is absolute value, I can ignore this -1 and take the limit of this series. Remember, the absolute value is still needed because I don't know what x is. Now when I take the absolute value of x over 5 to the k power, I can take the exponent k out from the absolute values. Whether it's inside or outside of the absolute values will not change that absolute value. Now when I do my root test, the limit is k goes to infinity of the kth root of the absolute value of x over 5 to the k. The kth root and the exponent k cancel. This becomes the limit as k goes to infinity of the absolute value of x over 5. Do I need the absolute values on 5? No, I don't. But you can keep them on if you wish. Notice that there's no k in this expression. So as k goes to infinity, the absolute value of x over 5 is simply some constant. So the limit is absolute value of x over 5. Or if you want to pull that absolute value of x out, it may be clearer to see that the limit of 1/5 is simply 1/5. So this limit is absolute value of x over 5, which will converge as long as this is less than 1. Okay, so again, we're always comparing it to our geometric series where convergence is whatever that limit is, has to be less than 1. So when we solve, we get the absolute value of x is actually less than 5 by multiplying both sides by 5. So the possible interval of convergence would be -5 to 5, or in interval notation, parentheses -5 to 5. But this is just a possible interval of convergence. I still need to check the endpoints. Now, I didn't have to check the endpoints on the previous example because the interval of convergence was negative to positive infinity. There are no endpoints. But here I have specific numbered endpoints, -5 and 5. So I'm going to go back up here and I'm going to check my endpoints to see if I can include them when I look at my interval of convergence. So when you check your endpoints, the first one I'm going to check is the -5. What you're doing is you're putting in that value for your x value into your original series because that's where we're determining convergence. So I will have k equals to 0 to infinity of -1 to the k, -5 to the k, over 5 to the k. Notice if I were to simplify that, the -1 to the k, -5 to the k, I can multiply that to get 5 to the k. So this is 5 over 5 to the k. And I have my series 1 to the k power. This is a geometric series with r equal to 1. So since r is not, the absolute value of r is not less than 1, this series diverges. So it's a divergent geometric series. Since x equal -5 makes a series diverge, I cannot include it in my interval of convergence. So let's try x equal to 5. If we put x equal to 5 in our series, it's k equal to 0 to infinity of -1 to the k, 5 to the k, over 5 to the k, and you see that the 5 to the k in the numerator and denominator will cancel, which means this is just -1 to the k. We have this alternating series, so we could try to see if it diverges by doing the divergence test, or we could check properties of alternating series. So remember, this is like times 1. If we were to take the limit and use divergence test, we would ignore the -1. If we're going to use alternating series, we still ignore the -1, and we would check the properties. So the first property, well, the two properties are check the limit and check to see if it's non-increasing. I'm going to do the limit first, because if the limit is not equal to 0, then I can just assume by divergence that it diverges. So if I take the limit as k goes to infinity of, remember we're ignoring the -1, we're just taking the limit of our a sub k, which in this case is 1. So when I take the limit as k goes to infinity of 1, the limit is 1. And since it's not equal to 0, I can say that this diverges by, and we'll use divergence test. So when x is equal to 5, our series diverges. That tells me that my interval of convergence is simply -5 to 5, where my radius of convergence r is equal to 5. Now let's go back to when I solved and I got the absolute value by itself. So since I got the absolute value of x less than 5, that actually tells me that my r is equal to 5. And this brings us to this theorem with power series. Whenever we're determining convergence of a power series, and here we're looking at a power series that has any center A, it's going to converge in one of three ways. First way, it can converge absolutely for all x, and that's what we saw in that first example, example 1a. We saw that the interval of convergence is negative infinity to positive infinity, and in that case our radius of convergence is positive infinity. It could happen that it converges for the absolute value of x minus a less than some number r. So remember, we had absolute value of x less than 5. In that case, our a would have been 0, and then our r is 5 if we compare it to this theorem. So we can converge absolutely for some absolute value of x minus a less than r. And in that case, the radius of convergence is this number r. The third case, which we didn't do an example on, would be that it converges only at the center A. And in that case, the radius of convergence is 0. So remember what we were using. We were using the root or the ratio test, and we were looking at that limit. Then this third case, if you compute the limit, and you get that the limit is equal to infinity, remember that would be like the absolute value of x times infinity. It really doesn't matter what x is. This will always be greater than 1, right? Because you need to have whatever that is less than 1, which cannot happen if the limit is infinity. The only time it will be less than 1 is if x is, in this case it would be 0, but if you had an x minus a times infinity less than 1, if x was equal to a, then that value would be 0. 0 times infinity is 0, which is less than 1, which means it only converges at the center A. The radius of convergence is 0. Why don't we do another example? In example 2, we're actually told to use the ratio test to find the interval and the radius of convergence. Oftentimes you will be told which test to use. Because when I look at this series, my first instinct would be to probably use the root test because I see the exponent k. But it turns out that the ratio test would probably be more efficient, which is why it's included in the directions. So notice we're starting with 1, which is fine. That doesn't change our convergence. And we're using the absolute value of our series x minus 3 to the k over square root of k. So when we take the limit, as k goes to infinity, of the absolute value of the k plus 1 term over the k term, it's going to be x minus 3 to the k plus 1 divided by the square root of the k plus 1 term, all over x minus 3 to the k over the square root of k. Rewriting this, I have x minus 3 to the k plus 1, and I'm going to go ahead and separate it as x minus 3 to the k times x minus 3 over square root of k plus 1 times the square root of k over x minus 3 to the k, still in absolute values. I can see that the x minus 3 to the k's would cancel. And notice I still need the absolute values around the x minus 3 because I don't know if that's going to be negative or positive. So this limit as k goes to infinity, I need the absolute values on the x minus 3. I do not need the absolute values on the k, the square root of k, or the square root of the k plus 1. Now the absolute value of x minus 3, if I choose, I can pull that out in front. But you don't have to. It's just if it's distracting. And then when I look at the limit as k goes to infinity of what's left over, it's going to be infinity over infinity. So in indeterminate form, I could use L'Hopital's, or I could simply note that they're both square roots. So I could put it all under one square root. Now when I take the limit, I still get the square root of infinity over infinity. But now what I can do is I can go ahead and divide the terms by k, top and bottom, to get the limit as k goes to infinity of the square root of 1 over 1 plus 1 over k. And now I could see as k goes to infinity, the 1 over k is going to go to 0. This limit is simply the square root of 1, which is 1. So 1 times, maybe I'll just do it here, so I don't have to rewrite this whole thing. So this limit is actually x minus 3. So notice that this is going to converge provided that the absolute value of x minus 3 is less than 1. So this, in this case, my center looks like it's going to be 3. And my r is 1. So remember, when we get rid of absolute values, if you have an absolute value less than a number, it's always between the negative and the positive. So if I algebraically just add 3 everywhere, I get 2 less than x less than 4. So I could see that my center is 3. If I add 1 to 3, which is my radius of convergence, if I add 1, I get to 4. If I subtract 1, I get to 2. The interval from 2 to 4, this is a possible interval of convergence. I still have to check my endpoints. So let me go back up and check my endpoints. I'm going to first start with x equal to 2. When x is equal to 2, this series from k equal to 1 to infinity will be, so putting in 2 for x, it becomes negative 1 to the k. Over the square root of k. So this is an alternating series. If I take the limit as k goes to infinity, remember I'm ignoring the negative 1, so it's just 1 over the square root of k. And this limit is 0. So it meets one of the conditions for alternating series converging. The other condition is that I need to check to make sure that it's not an increasing series. So when k is equal to 1, I'm at 1 over 1. When k is equal to 2, I'm at 1 over the square root of 2. When k is equal to 3, I'm at 1 over the square root of 3. So notice that as my k values get larger and larger and larger, the whole expression, 1 over the square root of k, is actually getting smaller and smaller and smaller. So this is not an increasing series, so it's non-increasing. Which means it converges by the alternating series test. So I'm just going to put alt series. So it did converge at 2, which means that when I list my interval of convergence, I can include 2 as an x value that will allow this to converge. So let's check when x is equal to 4. When x is equal to 4, this series from k equal to 1 to infinity would be 4 minus 3, so it's just 1 to the k over the square root of k. I'm going to rewrite this 1 to the k as simply 1, and k to the 1/2 is a p-series, where p is equal to 1/2. And since that's less than or equal to 1, it diverges. So we have a divergent p-series. When x is equal to 4, my series does not converge. So now my interval of convergence is include the 2, but not the 4. And then my radius of convergence is simply 1. Let's do a little bit of a summary. When you're determining your interval and radius of convergence, you're going to use the ratio or root test to find your interval, where A is your center and your radius of convergence is R. So we're always using this property that absolute value of R less than 1, the convergence from geometric series. And then we have these 3 possible cases. If your radius of convergence is infinity, then the interval is negative infinity to positive infinity. If R is 0, then the interval of convergence is just your center A. If your radius of convergence is any number between 0 and infinity, then you'll have an interval of convergence where you're just adding and subtracting your radius of convergence from your center. However, you do have to check endpoints. The next thing we're going to do is we're going to look at what happens when we combine power series that actually do converge. So sometimes you can get away with not going through the ratio or the root test if you are working with series that you know converge and you recognize that they're combined. So let's suppose that we do have these 2 power series, and they converge absolutely to these functions. So remember, the power series are equal to some function. If you look down at example 3, we have this power series equal to 1 over 1 minus x, which is a function of x. So let's say we have the case number 1. Let's say that you're adding, subtracting the coefficients on your power series. So you're adding and subtracting these 2 convergent series. Then you're just adding and subtracting the functions that they converge to on this interval. So notice this interval did not change. That's the interval of convergence, which is nice because that means that you don't have to check endpoints. The interval has not changed. If it included the endpoints in the beginning and you added, subtracted these 2 convergent series, then it's still going to include endpoints. The second property says that if you take any convergent series and you multiply it by some power of x, and here we do have to be careful that this m value is an integer. Notice that k is an integer. K is always an integer. So make sure that m is also an integer, and that for all the terms in your series, when you add k plus m together, you don't get anything negative. So if it meets these criteria, then what you can do is bring the x inside the series. And whenever you multiply with the same base, you add the exponent. So just properties of exponents say that it's going to be equal to the x to the k plus m. So when it converges, it's still going to converge to this x to the m times the function that it converged to. The interval of convergence has not changed. We do have to be careful that x is not equal to 0, because remember, when x is equal to 0, that's kind of a special case. So when x is equal to 0, the series does converge, but you do have to compute this limit as x goes to 0. The third property we have is the composition, and we tend to use this one a lot. So let's say you have this function that's going to be some constant b times x to some exponent m. M is a positive integer. B is a non-zero real number. So what you can do is you can compose your power series by just plugging in this function h into your power series. That will also converge to f of h. The interval of convergence has not changed. So this is a lot of blah, blah, blah. It really doesn't make any sense until we look at some examples. So let's look at example 3. We have our power series 1 over 1 minus x, so that's just x to the k. So I'm just going to call that my function, f of x. So this series converges to 1 over 1 minus x, which is a function of x. Its interval of convergence is the absolute value of x less than 1. In part A, I have this expression 1 over 1 minus 3x. So notice I don't have x, I have 3x. Well, we could look at that 3x as my h of x. So this is going to be 3 times x to the exponent 1. So comparing that to property number 3, I can see that my m is 1 and my b is this non-zero real number 3. So by property 3, 1 over 1 minus 3x is going to be equal to the series that's listed above. All I have to do is simply substitute my h of x for my x. So instead of x, I just plug in 3x to the k. And it's that simple. I'm done. I found the series. I need the interval of convergence. However, all I have to do is substitute in 3x for x. The interval of convergence did not change. I'm still looking at the absolute value of x less than 1. I'm just substituting in 3x wherever I see x, which gives me the absolute value of x less than 1/3. So my interval of convergence is going to be negative 1/3 to positive 1/3, and I do not have to check the endpoints. However, if you get confused and you're thinking, do I have to, do I not? It doesn't hurt to check the endpoints. If you did plug in negative 1/3 into that series 3x to the k and positive 1/3, you would find that it will diverge at both endpoints. Let's look at B and see if we can come up with a series and find the interval of convergence. When I look at B, I see the x to the third. If I were to rewrite this as 1 over 1 minus x, I can clearly see that the 1 over 1 minus x is my function, which I called f of x. So this looks like property number 2. It looks like I have x to the third times this series, k equal to 0 to infinity, of x to the k. In this case, m is equal to 3. Notice that if I add m to any of the k values, and here I'm starting with k is equal to 0, then I get m plus k is always greater than or equal to 0, right? Because I'm starting with k is equal to 0, and then the k's just get larger and larger and larger. M is always equal to 3. So because those conditions hold, what I can do is I can just bring in this x to the third and simply add the exponents. To get k plus 3. My interval of convergence is still the same. My interval of convergence is still -1 to 1. And that's because I still just have an x here. Changing that exponent did not change the interval of convergence. What we're going to do next is we're going to look at some other properties with our power series. One thing we can do with our power series is we can differentiate, take its derivative, and we can also integrate a power series. So let's say that we have this power series, and we'll call it f of x, and it converges. So the important thing here is that your power series is convergent. If it does converge, then this series is differentiable and continuous on its interval of convergence. And to find the derivative, all you have to do is differentiate the power series term by term. And this is not highlighted or bolded in your textbook. I'm bolding this. And you'll see why in just a little bit. That's the important part. So since this is a power series, f prime is going to be equal to the series where, remember it's a polynomial, you would just bring the exponent in the front and subtract 1 from the exponent on the interval of convergence. The thing is, you got to be really careful. If you're going to use that property, you have to first note that your power series is written in this form. Notice that the coefficient on x is just 1. That's going to be really important. So if you can't get it so that your power series looks exactly like the one given, then you can't simply use that derivative. What you then have to do is expand it out term by term. Take the derivative of each term. And that's going to be the same when we integrate a power series. We can integrate term by term. And notice that whenever you integrate a polynomial, all you're doing is adding 1 to the exponent and dividing by the k plus 1. It's an indefinite integral, so we have this constant c that we're going to have to solve for. So you can also integrate term by term. And unless your series looks exactly like the one that's given as our f of x, then you can't simply use the property. You use the term by term. Nowhere in this theorem does it talk about this interval I of convergence remaining the same. So something else that is very important is you still need to check endpoints. So whenever you take the derivative or the integral of any series, you have to check the endpoints on the interval of convergence. Example 4, we're given this function g, and we're going to use f to see if we can find a power series for g. And it says to either differentiate or integrate f to find the power series for g. We also have to state the interval of convergence. So again, reminder, interval of convergence, it's like your domain. So I don't know if I have to differentiate f or integrate f. But what I do know about f, I don't want the the big one. What I know about f, and this is from the previous examples, is that it's equal to this series from k equal to 0 to infinity of 1 minus 2x. All we're doing is replacing x with 2x. And this was from our previous theorem when we were combining power series. To the k power. So the interval of convergence is the absolute value of 2x less than 1, which is the absolute value of x less than 1/2. Or in other words, my interval of convergence is -1/2 to +1/2. Now I don't have to check the endpoints because I used that theorem that said the interval of convergence remains the same. Okay, so I know what the power series for f is, and now I can use that to find the power series for g. Unfortunately, 1 over 1 minus 2x squared does not look like anything from 1, 2, or 3 criteria when I was combining power series, so I cannot use that theorem. So instead, what I'm going to do is either take the derivative of f or the integral of f and see if it looks similar to g. So notice that if I take the derivative of f, it's going to be, maybe it's easier if I write this as 1 minus 2x to the -1. It's going to be -1 minus 2x to the -2 times the derivative of the inside, which would be -2. When I look at the derivative of x, and I rewrite this, the negatives cancel, and I simply get 2 over 1 minus 2x squared, which is very similar to g. The only difference is the 2 in the numerator, which is not a problem, because I can see that g of x is simply 1/2 times f of x, right? If I times, or f prime of x. If I simply times f prime of x by 1/2, I get my g of x. So if I know the power series for f prime, then I would simply multiply that power series by 1/2 to get the power series for g. Unfortunately, f, the power series here, this 2 times x, the coefficient on x is not 1, so I can't just simply take the derivative of this series and call that f prime. What I'm going to have to do is expand it out term by term and then see if I can find a pattern to define my series. So what I'm going to do is I'm going to look at f of x. I'll leave a little space after the equal sign. I'm going to expand the terms out on the power series 2x to the k. So if k is 0, we have 1 plus, if k is 1, this is 2x. I'm going to leave parentheses around the 2x. Plus, if k is 2, I have 2x squared. Then I have 3x squared. Oops, 2x squared to the third. Sorry, I can't do math. Plus, I'll go one more, 2x to the fourth, and so on. So that's the pattern if I were to expand out the power series for f of x. So all I'm going to do is take the derivative with respect to x on both sides and see what it looks like. When I take the derivative of 1, that's 0, plus the derivative of 2x is 2, plus the derivative of 2x quantity squared would be bring the 2 in the front, chain rule, right? 2x stays the same, minus 1 from the exponent, times the derivative of the inside. And I'm not going to simplify that because my goal here is to find a pattern. So 2x to the third power becomes 3 times 2x squared times 2 plus 2x to the fourth power becomes 4, 2x to the third times 2, and so on. So this is what my f prime of x is. Now I just have to figure out what the pattern is so I can write my series. What I do notice is that the first term 0 cancels. I also notice that every term has a 2 in it. So what I'm going to do is I'm going to factor out the 2 and see what's left over. It looks like it's 1 plus 2. I'll leave this 2 in the front and I'll cancel out the 2 in the parentheses on each one of these terms. 3 times 2x quantity squared plus 4 times 2x to the third, and so on. So I'm just looking at what's inside the parentheses and seeing if I can figure out a power series for that with respect to some k value. Let's see, so this is 1, 2, 3, 4, and so on. So if I start with k is equal to 1, that would be like a k value. However, also notice that this is exponent 1, 2, 3, and so on. This would be like an exponent 0. So this is like 2x to the 0 power. So I can either define my k in terms of the exponent or in terms of the coefficient 1, 2, 3, 4. And I choose to define my k in terms of the exponent. So if I start with k is equal to 0, then I'll have 2x to the k. So that gives me the 2x to the 0, which is 1, 2x to the 1, 2x to the 2, and so on. But then I need that coefficient, the 1, 2, 3, 4. Well, if k starts at 0, then it looks like it's k plus 1. This is not unique, right? Whenever we come up with series, you can describe them in any way that you choose. However, this is one description of my derivative. And remember that g of x is equal to 1/2 times f prime. Oops, forgot to put to infinity. And I'll put the k plus 1 first because I like it that way. And then here the 1/2 and the 2 would cancel, which means this is my series for g. You may always reindex. So if you prefer to start with k is equal to 1, that's fine. Then you would just have k times 2x to the, if you're starting at 1, the exponent on the 2x would be k minus 1, which is perfectly fine. So I found my g of x. Now remember, my interval of convergence did not change, but I still have to check endpoints. So when x is equal to -1/2, I'll do that first. I'm checking in my g of x to see if -1/2 will make g of x converge or diverge. So I'm starting at 0 to infinity. If x is -1/2, this becomes k plus 1 to the -1 to the k power. We have this alternating series. The limit as k goes to infinity of ignoring the -1, we're looking at the k plus 1 is equal to infinity, so diverges. And this would be by the divergent test. So I cannot include the -1/2. Let's look at the +1/2. If I put in the +1/2, well, I don't want to have an equal sign there. That's going to irritate me. Then I have my series, k equal to 0 to infinity of 1 to the k. k plus 1. So this 1 to the k is gone. And then if we use divergent tests, the limit as k goes to infinity of k plus 1 is infinity, so diverges. Which means that I don't include the endpoints -1/2 and +1/2. So my interval of convergence is -1/2 to +1/2. This problem did not ask for the radius of convergence, so I can just stop here. We're going to look at one last example in this section. Again, we have this function g of x. The directions are all the same. G of x is the natural log of 1 minus 3x. F of x is the function 1 over 1 minus 3x. And I know the power series. Again, I know the power series representation. And that would be 3x to the k. Again, the interval of convergence is absolute value of 3x less than 1, which would be absolute value of x less than 1/3. And I'm looking at -1/3 to +1/3 as my interval of convergence. Now, when I take my g and I look at the derivative or the integral of f, the interval convergence will not change. However, I still have to check endpoints. So I have to find a relationship between g and f. Something that I do notice that if I integrate f of x, it will be the integral of 1 over 1 minus 3x dx, which reminds me of natural log, right? If I do a u substitution on the denominator 1 minus 3x, then I'll get 1 over u, which is natural log, and g is a natural log function. So that tells me that I'm probably on the right path. So du over dx is going to be equal to -3, or in other words, du over -3 is equal to dx. And now in my substitution, it's going to be 1 over u times du over -3, which I'm going to pull out the -1/3. Kind of skipping steps here because we did all that in previous chapters, not necessary here. Just look at the major steps. That's going to be -1/3 times the natural log absolute value of u plus c. And then when I substitute back in for my u, this is an indefinite integral, I have to substitute back in. That's going to be 1 minus 3x plus c, which is very similar to my g. The only difference is that with g, there's no absolute values. However, when I do finally write my series, usually we start with k is equal to 0 or k is equal to 1. It should be okay. Yeah, it'll still be defined. So now this series here for f, I'm running into the same problem that I had in the previous example. I have a coefficient 3 times x. So I can't simply integrate the series by doing the k plus 1 over the k plus 1. What I need to do is expand out and find a pattern like I did before. So I'm going to leave a little bit of space on my f of x equal to. When I expand out my series, it's going to be 1 plus 3x plus 3x quantity squared plus 3x to the 3rd, and so on. I'll go to the 4th. So now I'm going to integrate both sides with respect to the variable x. And when I integrate, the integral of 1 is simply x plus integrating 3x becomes 3x squared over 2. Integrating 3x quantity squared. Remember, this is 3 squared times x squared. So the 3 squared is a constant, it stays. I'm just going to write 3 squared. The x squared is going to be x to the third over 3. Now I'm not multiplying it out. I'm keeping it as 3 squared because my goal is to recognize a pattern. 3x to the third is 3 to the third x to the third. So the constant 3 to the third stays. X to the third becomes x to the 4 over 4 plus 3 to the fourth times x to the fourth becomes 3 to the fourth x to the fifth over 5 and so on, but I have a constant c because I integrated. Okay, let's see if we can recognize a pattern so that we can write a power series. Let's see, I have an x to the 1. I can look at that as like over 1. So I notice a pattern with the exponents. I have a 1, 2, 3, 4, 5. And that corresponds to the denominator 1, 2, 3, 4, 5, and so on. So it looks like I could start at k is equal to 0, but if I start at k is equal to 1, then this is simply x to the k, but I have to be careful because I also have these powers of 3, right? This is a 1, 2, 3, 4, and so on. Notice that the exponent on the 3 in the numerator does not match with the exponent on the x. Also notice if I write this as 3 to the 0 in the first term, then my exponent on 3 would be k minus 1, or is it k plus 1? And it looks like it's 3 to the k minus 1. So again, when k is equal to 1, the first term has a 3 to the 0. And then the x values correspond to my k values. And then in my denominator, the 1, 2, 3, and so on, also corresponds to my k values. So this is not unique, right? Because I could have started with k is equal to 0 and defined this in a different way. But what I would like to note is that this is what this series is equal to, provided this constant is 0. If that constant is anything else, I would have to add some constant to this whole series. All right, so let's see where we're at. Going back to the beginning, if I take the integral of f of x, it's equal to negative 1/3 natural log of 1 minus 3x. If the c value is 0, then this looks a lot like g of x. So my g of x, and I don't really care about the absolute values, my g of x is actually negative 3 times the integral of my f of x, provided I let my constant c be 0, which means my g of x is equal to negative 3 times my series from k equal to 1 to infinity of 3 to the k minus 1 x to the k over k. And I'm done with my g of x. However, I do note that I'm multiplying this series by a -3, and I see that I have powers of 3 in my power series. So if I were to bring, and I'm going to ignore the negative and I'm going to leave it on the outside, if I were to bring the 3 in, this then becomes 3 to the k. So I'm only doing this because it looks like it simplifies as the negative series from 1 to infinity of parentheses 3 to the x to the k power over k. Notice it in my original series, if I had just integrated the series 3x to the k, I would have gotten 3x to the k plus 1 over k plus 1, which is very similar except for there's no negative, and I'm a little off with my index. Now if you wanted to start with k is equal to 3, that's fine. You can always re-index. So if I were to subtract 1 from my starting k value, I could add 1, and it would be to the k plus 1 over k plus 1, which is fine. It would be very similar as if I were to take the integral of my original power series, except for I'm a little bit off, which is why my caution is that if your series, your f of x, does not match up to an exact power series, then integrate or differentiate term by term, recognize a pattern, write a power series. I do have my g of x. I know my interval of convergence has not changed. It's still -1/3, +1/3, but I still have to check my endpoints. So at this point, I'm just going to box in my g of x and check my endpoints. When x is equal to -1/3, the series, and here, remember, I'm checking this with g of x. It's going to start with k is equal to 1 to infinity. If x is -1/3, this becomes -1 to the k over k. This is an alternating harmonic series. It's going to converge. I don't even have to check anything. So harmonic, alternating, it's going to converge. However, it is harmonic, so if you didn't recognize that it was an alternating harmonic, you could check the limit. It's going to be 0. You could check to see that it's not increasing, and it's not increasing. So it converges by alternating series test. Now when x is equal to 1/3, this series is the harmonic series. It's 1 over k. Because it's 1 to the k power, which is just k, or just 1. So this is harmonic. Harmonic diverges. Which means my interval of convergence can include the -1/3, but it cannot include the +1/3. And that's it for this section.